Hi, this is Arash and welcome to the Epoxy channel. In this channel, we're going to talk about the epoxy resins from the theoretical aspects to the most practical ones. So if this is the first video that you're watching, or if you're interested in epoxy resins, please like and subscribe to our channel for more videos. Today, I'm going to talk about dispersant and wearing agents for epoxy resins. Dispersants are used to disperse pigments and other additives, reduce the impact of curing, and to impart improved end-use properties into epoxy systems. For example, in addition to pigment dispersion, the dispersants have been used to enhance the dispersion of CNTs in the epoxy systems, which has enhanced their final properties. For thermoset systems like epoxy resins, dispersants are aimed to interact with the resins, but the functionality of the dispersant should not interact with the functionality of the resins, and therefore it should not interfere with the desired curing process. Both good stability and good dispersion are required when dispersants are considered for epoxy resins. However, to obtain both features in one system is often a hard task. For example, it is possible to reach a stable low viscosity dispersion, but often with poor dispersion quality, for example, pigment float issues. On the other hand, a good quality, high color strain dispersion is often unstable and is difficult to compound. That's why dispersion agents are often designed especially for a certain system or a certain filler. Means that various small quantities of dispersing agents are usually needed for the epoxy formulations. Dispersed epoxy systems contain at least two separate phases: the binder epoxy resins, which is liquid, and the solid pigment. These systems offer very large phase boundaries, which separates these immiscible phases. In other words, a dispersion or a dispersed system contains two phases which are finely divided: a discontinuous dispersed phase or an inner phase, and a dispersion medium, continuous phase. The phase boundary exists between the dispersed phase and the dispersion medium. This phase boundary chiefly determines the final properties of the dispersed systems. In case of liquid dispersion medium, for example a resin, if the dispersed phase is a liquid, the system is emulsion, for example silicone resin emulsion, and if the dispersed phase is a gas, it is a foam. Here the focus is on liquid-solid systems in which the dispersed phase is a solid, for example pigments and fillers. In these systems, the particle size of the dispersed phase is also a characteristic feature. If the particle diameter range from 5 to 1000 nanometers, for example fillers, the dispersion is called a colloid. In colloid, the inner phase boundaries determines the properties of the system. The dispersed phase can also be polymer particles, often 50 to 5000 nanometers. It should be mentioned that the atoms or molecules of the surface of the particle have a higher energy content than those inside it. Therefore, the size of the particle is an important factor in colloids. Therefore, colloids have a large surface or interface area and have a high energy content. Another crucial factor in colloids is the stability of the dispersions. The association of dispersed particles in the medium is called flocculations. Flocculation reduces the phase boundary between the particles and the dispersion medium and makes the dispersed systems to be thermodynamically unstable. Inorganic pigment and fillers are mostly charged, and as the overall dispersed system is uncharged, for stability, the liquid phase must contain an equal number of counterions in close proximity to the particles. In electrostatic stabilization, an ion cloud exists around the particle, which similar charges around the particle prevent the flocculations because of the electrostatic repulsion. It should be mentioned that here van der Waals forces counteract the electrostatic repulsion, and therefore a large sphere of anion is more favorable for stabilization. Moreover, adding electrolyte salts to these systems cause counterion of the ion cloud and promotes flocculation, and therefore it is important to avoid any electrolyte or salts in waterborne systems. The surface of pigment or fillers particles can acquire the charge in several means. For example, by dissociation of functional groups on particle surface, or by the absorption of ions, mostly polyions. In a certain pH value of the medium, the surface charge is become zero, which is called the isoelectric point. In other words, above the isoelectric points, the particles are negatively charged, and below it, the surface is positively charged. Therefore, the density of electric charges increases as the difference between the pH of the dispersion medium and the isoelectric point is increased. Due to the high dielectric constant of water, electrostatic stabilization is especially important in waterborne systems. The other type of stabilization is steric stabilization. Here, the colloids are stabilized by adding water-soluble polymers, for example, protective colloids such as polyvinyl alcohol. In this type of stabilization, the system is insensitive to the addition of electrolytes. Practically, the addition of suitable polymer is the only way to stabilize dispersions in organic media, which the polymers are absorbed on the surface of the dispersed particles and result in dispersions. Surfactants, also referred to as wetting agents with larger molecules, may also act as steric stabilizers depending on their size. Polymers are more suitable for inducing steric stabilization. First of all, they must be able to be strongly absorbed on the pigment surface, which occurs by the presence of appropriate functional groups, also called anchoring groups. Moreover, the presence of long macromolecular chains that dissolve in the dispersion medium is a must for these polymers. However, there is a risk for polymer coiling and subsequently flocculation if the medium is poor solvent for the polymers, for example. On the other hand, the risk of bridging, flocculations, incompatibility, and high viscosities also exist. If the molecular mass of these polymers is too high, these risks are there. The molecular masses of these polymers is often in the range of 1,000 to 15,000. Practically, often no definite distinction between wetting agents and dispersing agent is provided by the suppliers. However, this guide can be used to distinguish between these systems. Wetting agents, also called surfactants, are low molecular weight amphiphilic substances, and dispersing agents are oligomers or polymers that stabilize dispersions of particles against flocculations. Polyanions can be served as dispersing agents in dispersing systems and acts by increasing the repulsive forces and therefore promotes the electrostatic stabilization. They are absorbed primarily on the electrically charged inorganic pigment and filler surfaces. In this case, the electrostatic stabilization is achieved by several means, including an increase in like charges, charge reversal of oppositely charged pigments, prevention of co-flocculations, or in some cases, the complexation of multivalent cations. Polycarboxylates, mostly salts of carboxylic acids, linear polyphosphates, and cyclic metaphosphates are examples of polyanion dispersing agents. Polycarboxylates have hydrolytic resistance and show good comparability, resulting in good film quality. However, they have a higher cost and need a higher adhesion level, and also are sensible to multivalent cations. On the other hand, polyphosphates have comparably lower cost and low adhesion levels, for example 0.2 to 0.5 weight%, and are not sensible to multivalent cations. However, they show slow hydrolysis to monophosphates, and also soluble phosphate salts may lead to dilution and crystallization of the coating. Finally, in latex paints, often a combination of polyacrylates and polyphosphates are used. The schematic of salts of a polyacrylic acid dispersing agent for waterborne system has been presented here. There are also polymeric dispersing agent for steric stabilization. In this case, black and graph copolymers are better suited to stabilization than random copolymer or homopolymers. It is worth repeating that here the risk of bridging flocculation should be considered. Moreover, the dilution of sterically stabilized pigment dispersion with unsuitable solvent result in coiling and consequently flocculations. Pigment separation is another issue that has to be considered. When dispersion is not good, separation of pigments might happen. There are two different types of pigment separation: vertical pigment separation or floating, and horizontal pigment separation or flooding. In floating, there is a local difference in the concentration of the paint surface resulting in a non-uniform color. In flooding, the color is uniform. However, there is a perpendicular difference in the concentration of the color on the surface. Separation of pigments may happen because of different pigment densities and can be avoided via controlled flocculation. Wetting agents or surfactants are surface active or amphiphilic compounds that are employed to decrease the surface of interfacial tension at phase boundaries and consequently improve wetting. Salt of fatty acids or soaps, for example sodium stearate, are of examples of wetting agents. Sodium stearate is an amphiphilic compound that has a head-tail structures with both hydrophilic groups, carboxylate, and hydrophobic groups, long-chain alkyl. As the chain length is low, this compound cannot induce steric stabilization. Wetting agents improve wetting properties by acting at the phase boundaries and lowering the interfacial tension. Wetting agents are often classified into anionic, cationic, amphoteric, and non-ionic types according to the charge on their hydrophilic group. Based on the chemical structures of the hydrophobic groups, wetting agents can be classified as hydrocarbon, silicone, and fluorinated surfactants. The surface tension of the medium is inversely proportional to the hydrophobicity of the tail, and therefore this hydrophobicity determines the efficiency of the wetting agents. In other words, the more hydrophilic head, the less efficient surfactant. Although increasing the concentration of the wetting agent often results in further surface tension reduction in the aqueous solution or some solvent-borne systems. Also, increasing the concentration of the wetting agent often results in further surface tension reduction in the aqueous solution or some solvent-borne systems. However, the optimal adhesion level of wetting agent should not be exceeded. Otherwise, unwanted side reactions may occur, for example, undesired hydrophilicity of the coating or foaming. Solubility of the surfactant is another factor which has to be considered carefully. Table present the effect of hydrophobic group on surface activity or surface tension in water. It can be seen that it has been reduced upon the addition of the wetting agent. Examples of silicone and fluorinated surfactant have been presented here as well. Thanks for your attention. I hope you enjoyed this video. Please share your comments, thoughts, or questions, and I will come back to you soon. Thank you.